Next, we're going to define the model and instance data struct, which, serves as a core component for managing models and their instances. This struct includes a few key attributes. First, model ID, which is a unique identifier for each model and ensures that we can easily distinguish between the different models in our game. Then we have the instance IDs vector, which is super important for tracking those individual instance identifiers of the model, making it a breeze to retrieve and manage them. We also include a transformation matrix, which is a 4x4 matrix that manages the model's position, rotation, and scaling within our game environment. Now, this starts off as an identity matrix, and it gets updated as we apply transformations, which allows for those dynamic adjustments during gameplay. Finally, we have the instance count, which keeps track of how many instances of a particular model are currently active. Pretty valuable information, right? In the constructor of model and instance data, we initialize model ID with the given ID, set instance count to 0, and create an identity matrix for transformation matrix. This structure really lays the foundation for efficiently managing our models and their instances as we continue to build up the functionality of our model management system. Next, we will implement a class called Model Manager, which is essential for effectively managing our models and their instances. Now, this class uses an unordered map to store instances of model and instance data indexed by their unique model IDs. Super handy, right? So let's dive into how we can register our models. The register model method is designed to ensure that each model is registered only once. It does this by checking if the model already exists in the map, which prevents duplication and keeps our model list clean. This simplicity, trust me, is crucial for maintaining an organized state. Next, we are going to add an instance for a specific model using the addInstance method. This method pushes the new instance ID into the instance IDs vector and increments the instance count, ensuring that our records accurately reflect the number of active instances. Now, let's say some instances are no longer needed. That's where the removeInstance method comes in. It efficiently removes those instances by erasing the instance ID from the instance count, which helps us maintain precise tracking. To enable dynamic transformations, we can implement the updateTransformation method. This one updates the transformation matrix of a model, allowing for real-time changes based on gameplay mechanics. Pretty cool, right? And finally, the model data method is there to give you access to a specific model and instance data instance, providing the flexibility needed to manipulate or retrieve model attributes effectively. So, that's a wrap on setting up Model Manager and its methods. Now, let's implement the function to render multiple instances of our model efficiently. This function, renderInstances, begins by binding the vertex array object, or VAO, associated with the given model. Now, this binding is crucial for OpenGL to know which vertex attributes to use for drawing. Next, we generate and bind a buffer that will hold the transformation matrices for each instance. Using GL buffer data, we upload those transformation matrices to the GPU. This allows OpenGL to automatically apply these transformations during rendering, which optimally prepares our data for instancing. And you know what? This step really enhances performance because it minimizes the number of draw calls we have to make. The function then enters a loop where we call glil_drawArrays instanced, effectively drawing all instances of the model in one go. This method significantly reduces the overhead that usually comes with multiple separate draw calls, resulting in smoother frame rates, especially important when we're managing a lot of instances on the screen. Finally, we unbind the buffer and delete the instance buffer to free up resources once the rendering is complete. By managing instance rendering this way, we can maintain high performance while crafting visually rich environments in our game. Now, let's implement the applyTransformations method in our Model Manager class. This method is crucial as it allows us to dynamically update the transformation matrices of model instances, giving us the ability to make real-time adjustments based on game events or player actions. So, here's how it works. We start by checking if the model ID exists in our model's map. If it does, we retrieve the associated model and instance data. Next, we iterate through a vector of transformation matrices that we're passing in as an argument. For each matrix, we update the model's transformation matrix, but only if the index is within the bounds of the provided transformations and matches the current number of active instances for that model. This approach ensures that we can efficiently apply batch updates to multiple instances, which is essential for creating those dynamic scenarios in our game world. By managing transformations centrally, we enhance gameplay fluidity. Elements like position, rotation, and scaling can react instantly to changes in the environment or user inputs. This flexibility adds richness to the player's experience and deepens the interactions within your game, making it all the more engaging. Next, we will implement a class that provides a mechanism for managing instances efficiently, which, is crucial for maintaining performance in dynamic environments. The instance pool class introduces a simple yet effective instance pooling strategy to enhance memory management. So, within this class, we use two main collections: active instances, which tracks currently active instances, and available instances, a set that stores instances that can be reused. The return instance method allows you to deactivate an instance by not just removing it from the active list, but also adding it back to the available pool. This operation helps in conserving memory by preventing unnecessary allocations. On the flip side, the borrow instance method checks if there are any available instances when you need one. If an instance exists in the pool, it removes it from that available set and adds it to the active list, thus making it ready for use. But if no instances are available, it simply returns 0, indicating that all instances are currently in use. Through this class, we can efficiently manage memory and reduce garbage collection overhead, ultimately improving frame rate stability in the application. As we wrap up our exploration of dynamic management of models and instances, it's really clear that handling model data properly can add significant value to game development. We've taken a close look at how to effectively utilize the model and instance data struct, delved into instance rendering with OpenGL, and explored dynamic transformations along with memory management. Remember, having a solid grasp of dynamic model management not only boosts performance, but also enhances the player's journey through your game. As you continue on your game development path, implementing these techniques will empower you to craft more complex and engaging worlds. So keep on experimenting, keep coding, and most importantly, enjoy the thrilling process of bringing your game ideas to life.